Hi, everybody. Evening. Uh, Welcome to Rod's Office Hours, where you'll get some oil industry insights. Um, it was this week. We're going to talk about gas lift valves. It was great to see some of you face to face this afternoon at the Lunch and Learn here at the local service company shop. Um, and It's really great if you get a chance to go see a local shop or a local service company. There's lots of interesting work going on there. Always great to get out and see what's going on in the industry. Lots of great technology, lots of great things that you never hear about. It's always good to go see that stuff. And it was nice to meet a bunch of people there today. So we've been talking about artificial lift, and we've kind of covered rod pumps, ESPs, a little bit about plunger lift and PC pumps. And like I say, tonight we're going to speak a little bit about gas lift valves and gas lift artificial lift. And again, I really like artificial lift. It's as doing production engineering in oil and gas lift is a very versatile form of artificial lift used both onshore and offshore. And of course, just a reminder who I am. My name is Rod Gibbons. I've been a petroleum engineer and entrepreneur for the past 30 years internationally in oil and gas. And I work with my wife, and we've worked in a bunch of different places, and I've worked in the field, offshore, onshore, but also in the office, and I worked in a lot of interesting places with a lot of interesting people, and there's lots of opportunities in the oil industry, and I just want to share some of my practical lessons learned. This is not meant to be a theoretical sort of discussion. This is more application and how I've used it in my career. Just a note in the Q&A, if you have questions, just drop them in the Q&A. And as I got a couple of notes made in there on these videos going to YouTube, so you can see them there. And then, so if you just want to put something, have questions as we go, drop them in there, and I can pick them up and we can talk about it. There was a question last week around types of artificial lift and what's the most common types. So we've got rod pumps. We've talked about hydraulic pumps or jet pumps. We haven't talked about those much, but then electric submersible pumps, that was ESPs. So we had a good discussion on that last week. Gas lift is tonight's topic, and then there's plunger lift, which is kind of like gas lift with a little mechanical help, and then progressive cavity or PC pump, which is a sort of Archimedes screw. It's again rotating energy, so a little bit of a cross between ESPs and screw pumps, and you can actually get a downhole ESP PC pump, but that's not a big percentage of pumps. This is really good for solids. So, but one of the questions that we had was, what's like the most common types of artificial lift? And so this pie chart here, rod pump, 85. This is for US. Rod pumps are 85% of the types of artificial lift, followed by gas lift, and then at 10%, and then ESPs, electric submersible pumps, at 4%, and then the other types 5-6%. So dominantly rod pumps. This is by number of installations, and then gas lift and ESPs. And I would say, having said that, rod pumps are predominantly onshore, and there's a lot more wells onshore. Offshore is definitely dominated by gas lift and ESPs, but I would say the most common offshore lift system is gas lift. Just as a reminder, again, we're talking about artificial lift. The point of artificial lift, we want to get reservoir fluids from the reservoir to surface, and we've gone through previously our inflow performance curve and our vertical lift profile. When they don't match, the well doesn't flow naturally, so we have to use artificial lift. And so pressure equals the density times gravity times height. And again, here we have, blowing bubbles into our column of water, lightens the fluid column and puts it higher up. That there's no better form of lift that exemplifies that than gas lift, because this is exactly what we're going to do. Is we're actually going to bubble in gas into our fluid column using the well architecture to actually lift reservoir fluids. So what does a gas lift well look like? Well, this is a simple wellbore diagram. Your casing strings, again, with these little triangles showing the casing points. This example has a liner in it. You've got your reservoir and your pay zone here, fluid coming in. Most gas lift installations have a packer on the bottom, so a production packer. So that seals off the annulus of the well. So the tubing and casing, the space between the tubing and casing, the annulus, is sealed off from the reservoir. And what we do is we put gas down the annulus of the well, and then it goes in through these little valves and lifts production fluid up the tubing. So I guess the critical components of that system, well, so this is a skid gas compressor. And so when we produce oil, or we'll get gas, because there's even a little bit of gas because it's in solution in the oil usually, or you can have free gas and water. So you'll separate that out at the surface, and then you'll have gas. Well, oil goes to oil sales, and then gas typically goes to gas sales if you have a gas pipeline. But you can also use some of that gas as fuel gas on your location. If you're onshore, on your location, on your platform, or FPSO if you're offshore. So and in this diagram, these red bubbles are the gas, and the blue is water and oil. So again, we're using gas as a fuel source for our operations. To get this gas to flow, and when we look at our IPR and our VLP, our lift curves, we want to have that surface pressure low so that the well will flow easier against the lower pressure. That's great to get the fluid from the reservoir up to surface. When it's at surface, well, now that I have my gas at surface and we've separated it from the oil, now that I have my gas at surface, well, now I want to get rid of it. I'd like to sell it. So I want to sell it down a gas pipeline. Well, the gas pipelines, they operate at a certain pressure. So you have to compress the gas, so pack it in tighter so that the pressure goes up, so that it will go down a sales pipeline. And if you happen to be in a place where there is no sales pipeline, then you probably have to re-inject the gas back into the reservoir. So, and that takes even more pressure. Back in the old days, you'd see a lot of times you'd see a lot of flares in the nighttime from the gas being flared off because oil is being produced, and then the associated gas would just be flared. That's a lot of places that's not allowed. Most places that's not allowed for obvious reasons. It's a waste of the resource. So you want to capture that gas and use it. Either you use it to produce more oil, or for consumers to use it, for customers to use it. So a lot of a gas compressor is a pretty critical piece of equipment in most facilities, onshore, offshore. This is skid mounted, so this would be an onshore skid, and so you have your control panel, some scrubbers to make sure the gas is nice and dry, and then what looks like a pump, but is actually pistons for compressing the gas. So we're really increasing that pressure. When we have that gas pressure pressured up, well, now it's a great tool for us to use to be able to use it to produce more fluid out of the wells. And we do that by putting high pressure gas back down in the annulus of these wells. And so if we just zoom in on, so this would be our casing on the outside here, and this is our tubing. So we're getting oil, water, and some gas, some solution gas coming up the tubing. And then here in red, this is gas with gas. We're pumping that, compressing it, and pushing it down the annulus. It'll reach the gas lift valve. And so it enters the gas lift valve and then goes into the tubing, and then basically what we're doing is we're blowing bubbles. And this drawing is a nice one because you can see the bubbles are quite small here, but as you go further up, the bubbles increase in size. And this is because the pressure is lower up here than it is down here. So the bubbles expand and actually lower your density. So bubbles lower density. And we know from our lift curves, pressure equals density times gravity times height. I'm not changing the height. I'm not changing gravity. But here, I'm reducing my density. And you can reduce your density a lot with gas lift. So, and why is it called gas lift? Because it's gas and it lifts the fluid. Again, by bubbles, by lowering the density of that fluid. So, and again, just graphically, here's our reservoir. We get some bubble, some oil gas coming in. Again, injection gas comes, we're pushing that down the annulus, comes into the valve, bubbles, and lifts this fluid up. And graphically, what does this look like? Well, if pressure is this way, and this is depth, well, so I have a gradient. And the gradient on this curve, pressure versus depth, is the density of the fluid. So this is density of gas, and then this is density of water or reservoir fluid. So you can see, again, this is another way of showing your inflow performance relationship. We remember that one. If we were to draw this straight like this is where we would be. We can't get back to surface. So again, we put enough gas in here to lighten the fluid column, reduce that density, and we can get the well kicked off and flowing to surface. And we'll touch a little bit on just some design curves and how you design the system. This is actually another fairly simple system to design, so which is good. So, but first we'll just talk about a few. So this all looks good on this cartoon and this graph. What what are what bits and pieces do you need? What nuts and bolts? And so, well, the first thing that you need is it's called a side pocket mandrel. And what a side pocket mandrel is we normally have just round tubing going down our well. But now we've got a bit of an issue. We got round tubing and we have our round casing outside of it. Well, but now I want to have a way to be able to put gas into the tubing, but I don't want reservoir fluids going back into the annulus. I want to keep them in the tubing. The primary reason for that is for well construction, for stuff that for pipe that is seeing flow from the reservoir, we want to be able to change that stuff out. If it wears out, if it has an issue with the chemistry, we can always change it out. We want to try and keep reservoir fluids away from the pipe that is permanently in place, such as casing. So there's a question here. Is the gas in the annulus for the gas lift system pumped through a control line, or is it pumped directly into the annulus? That's a good question. I'll just go back to probably this picture. So the annulus gas is actually pumped straight into the Christmas tree and straight into the annulus. So you can have control lines strapped to this tubing doing for hydraulics or for sensors or any of that sort of stuff. But no, we are using the full annulus volume. And these gas lift rates can be large. So a gas lift line, so a control line can be say 3/8 of an inch, ½ inch, so like 12 millimeter diameter. Whereas a gas lift line going to a Christmas tree is typically at least say 2-inch or 50 millimeters. So we're putting a lot of gas down here. So in my straw example, I bubble it gently. We're going to put a lot of gas down here, so we want to use the entire annulus volume. So you also want to make sure that your after you drill and complete a well, that your annulus is clean, and so it doesn't have any dirt or anything in it. So a good question. Yeah, we're going down the entire annulus and straight from surface, and that's for offshore, onshore, or subsea. You're basically from the tree down to the gas lift valve is full of gas in the annulus. And so then it gets down to the side pocket mandrel. And so, and here's so what we do is we take the tubing and we make it a little bit bigger so that we can fit this valve in there and still have enough flow path that we're not getting in the way of the reservoir fluids coming past this valve. So they call it a mandrel because it's not a full jointed pipe. It's sort of a shorter length of pipe, and then it's the side pocket. So you put the valve in the pocket, and then so there's a mandrel where the valve sits. Then there's the gas lift valve itself, and what the gas lift valve is doing is, as gas comes in, it opens the internal check valve and allows gas to flow through. Some have a double check, so then it puts pressure on that and allows gas to come in and go into the tubing and bubble out like what we just saw in the previous slide. So that works great in that direction. if you have a shutdown, or if you have a problem with your Christmas tree, for example, it gets a leak or it gets knocked off or something happens. What you don't want to have happen is you don't want your reservoir fluids to be able to go back out through this hole, out into the annulus, and then be able to flow to surface uncontrolled. So that's why there's these check valves put in place so that if the annulus pressure drops, the check valve seals, and sometimes there's two checks, sometimes there's one, so that reservoir fluids can't get back into the annulus for uncontrolled release. And another reason as well is the casing is our sort of foundation for when we're drilling and completing, but we don't want reservoir fluids to be contacting the casing because that can lead to corrosion or it can lead to scale or other issues. So again, we want to seal out. If we're not injecting gas into the tubing, we don't want reservoir fluids to be going back the other way. So that's basically, so it's a check valve system. So this is what a side pocket mandrel looks like. This will screw into a joint of tubing, and then it's about 1.5 times the size of a regular joint of tubing, so that it sticks out. The valve can fit into the side pocket, but this can still fit inside our casing string. So when drilling engineering, completion engineering, when you're designing your well, you're going to have a design flow rate, which will decide the size of your tubing. But if you expect to have to gas lift the well in the future, you're going to make that casing a bit bigger so that you can fit side pocket mandrels in. And there's a bit of a video on side pocket mandrels coming up. So then you have your valves. So we got our side pocket mandrel. That's where that stays in the tubing. It's screwed in. It's run with the tubing. The valves, again, a general philosophy. If there's something that has a lot of wear, a lot of use, it's great if you can retrieve it and change it out. So with gas lift valves, you don't have to typically you don't have to pull the tubing to pull the valve out. So because you've got gas coming in, opening this check valve and going in and then into the tubing. So, but that can move a lot of times in the life of a well. So it's always good to be able to pull it. There is, and so this is what a valve looks like. Go to the next slide. So you can see this is what it looks again. One of these things that looks like a piece of pipe, as always. What you have, and this is the gray here. It would be your side pocket. It would be in your side pocket mandrel, and there's holes in that side pocket mandrel. There's holes drilled in that mandrel, which allow gas to come in. So because you have gas from your annulus coming in through your side pocket mandrel. Okay, I want to control the flow of that gas, so I have packings or seal stacks on top and on bottom. So now I've sealed off. That gas is coming in, but it can't get past these elastomer packings. Then we got a hole in the valve. So gas comes in and then goes in through this hole, travels through the valve. There's a check valve here, and comes out the nose to go in, and then the gas comes around the corner and goes into the tubing. There's a latch on the top that's for pulling and running the valve. So it's a bit of a fishing net, so you can get on it and pull it out or set it. So I do have a, so this is an actual gasket valve. So this is an inch and a half is the diameter. So which is I would say kind of the most common size. And I just hold it up like this. You can see it's almost to scale. So this top part, this is just purely for pulling and running the valve. And then there's holes drilled in the valve here, just like on the diagram. That allows gas, when it comes in through the side pocket mandrel, to come into the valve. Then you have two seal stacks, an upper seal stack and a lower seal stack. That seals off in the mandrel to keep my gas where I want it. I want it to go through my valve. And then it comes out to these ports here and bubbles out through here into the tubing. So, and here's a valve. Here's an older valve that so you can see this is a different design, but this is the seal stack. Here's the holes, and there would be another seal stack. There's one ring left here. So again, this sits in the mandrel, same sort of way. And then we just have a look inside. We just now, so just an orifice, a hole, so the gas goes through there. And just like an O-ring. And then now, and this is the check dart. Normally this is round and there's a couple of legs on it, but as you can see, there's a reason why I have this valve is because it suffered a lot of damage. I don't have it here, but go back to the previous slide. So this is actually this check valve here. So it's supposed to be stopping the flow from going back out the annulus, but it has it's failed. So, but this valve also has a backup in the nose, the bottom of the part of they call it the nose, just because it sticks out like a nose. And so you can see here, there is here's a check valve that's intact. So you see it's nice and round, and it's got that pin on it. So, and again, put it back in here. Oops. Like that. That screws on the bottom. So, if the pressure drops in the annulus, this check dart stops any fluid in the tubing from getting back up the annulus. But when one breaks, then it's hard to, then you have to pull it because it starts to get in the way. Yeah. Question. In your opinion, as we move toward lower carbon operations, how is the energy intensity of gas lift compression being weighted against alternative lifting methods like ESPs and future NL developments? I ask because it could help shape my final project at MUN. Yeah, that's a good question, and I don't feel qualified. I don't think to give an answer for you to shape your final project, but I do feel that I mean, again, this is the whole conservation of energy. So if you're comparing, and I assume this is for offshore, if you look at a development offshore Newfoundland, which is where we're filming this tonight, then gas compression is required. You're going to produce the oil, and we currently don't have a gas export line or a floating LNG facility, for example. So we can use the gas on the platform or on the facility, but we have to re-inject it back into the reservoir to conserve the gas. And I think no one would argue that re-injecting gas is a better idea than just flaring it. And there's clear limits for the amount of flaring you can do. So if you are compressing the gas because you need to re-inject it to conserve it, then you're really talking about the energy efficiency of recycling the gas through a gas lift system, because we'll put this gas through the well and then we'll produce it back out again. So we're recycling that gas when it's on gas lift. And for an electric submersible pump, now we're actually taking that gas, burning it in a turbine and generating electricity with it, and then using the electricity to drive the electric submersible pump. So I think, I do think it's an interesting project to see which one is more, I think, being weighted energy intensity. Yeah, I think it is a good project to explore that. I think you're going to find that it's going to be much more CO2 neutral than we would be led to believe, because you're recycling a lot of the gas, and it's a lot of gas that we are currently storing. And so being able to optimize the resource by using for now it's a byproduct of what we're producing is a great solution. I'm going to guess gas lift is going to win, but interested to hear the results. Another question before installing the gas lift valve into the side pocket mandrel, how do we ensure the hole in the side pocket mandrel does not communicate? So before we install the gas lift valve in the mandrel, and I'll just go back up to our mandrel picture here. So right here, so this is a hole, and it's drilled in the mandrel, and so you can sort of see it here in this picture. It's like there'll be like 3 holes drilled. So there's nothing to stop that communication. So on initial completion, and you'll run the mandrel with the tubing string. So before the mandrel gets in, you'll have just your casing, and the mandrel's run with the tubing. So you'll have you can have communication tubing to annulus. If that is a concern, and at that time when you're running your completion, you shouldn't have reservoir fluids in your wellbore. You should be swapped over from drilling mud to clear brine or completion fluids, whatever's good for running the completion. You want to have nice clean fluid, so you're not going to have reservoir fluid in there. That's you have to have your well killed and conditioned before you run your completion. So we can live with communication at that point. Sometimes you will run the gas when you run the side pocket mandrel in the tubing string. You can have the gas lift valve pre-installed, so it's actually a sealing as it's being run in the well. That's I would say a very common way to to run gas lift valves, mostly for the reason it's already installed. You don't have to come back on the well and do an installation. So, especially for something like, say, subsea wells, where it's pretty pricey to come back. So, yeah, so we had a look at the check valve, the check port. Once we get reservoir fluid in the well, then we don't want to have stuff flowing out into the annulus. And this is a 1.5 inch diameter. You can get gas lift valves in 1 inch for smaller flow rates or different well conditions, but 1.5 inch is definitely the most popular. So we've got our side pocket mandrel and we've got our valve. Now there's one piece left in the system, which is the kickover tool. And all a kickover tool is it's an intervention tool. So you use it when you want to, if you wanted to pull an old valve or install a new valve. Well, you can't just drop it down the tubing because the valve's actually over to the side in the side pocket. So what a kickover tool does is it's for pulling and running the gas lift valves. So, and again, a very clever design. If your tubing is this big around, but your gas lift valve side pocket mandrel is this big around, you need to run through the small hole to get to the big hole. And so to do that, this piece of pipe looking thing is actually fits through the tubing, but there is a spring loaded arm that will come out when it has enough space to and they call it kick over. It springs out into the side pocket mandrel to get the valve. So again, you would set the valve and then you would pull your kickover tool back out. That's your intervention. This would be run on slick line normally. So it's a running and pulling tool, but it's not permanently installed in the well. You just have your side pocket mandrel and your tubing string, and then your gas lift valve. So setting a gas lift valve, and so this is a bit of a mock-up in a workshop. And so in the chain vise here this is a side pocket mandrel. So you see the shape, it's not quite round, it's a bit squished out. And then, but what they've done is they've cut part of the pipe away so that we can see what's going on with the kickover tool and the gas lift valve. So I'll just run this video. So these guys are running this tool into, so this is our kickover tool. And so normally this would be run on slick line. These guys are doing it in the shop just by hand. So you can see they ran past where the gas lift valve seats, and then they pull up, and there's an orienting key. So there's a little groove in the gas lift valve mandrel that orients it so that kickover tool is facing the right direction. And see, then you can see it spring loads and it's kicked over in the side pocket. And now you can see they're jarring down and they're just hammering the gas lift valve into location. These seals are very tight. Now that it's in place, then they just jar up, pull up, and the kickover tool is now released from the valve. And now the valve is set in the side pocket mandrel. Let's see if that. Yeah. So, and again, this is a shop demonstration, but really you're probably 1,000, 2,000 meters deep, and you're doing this with slickline. So, as you can see, it is ingeniously simple technology. Again, there's only one way for this kickover tool to pull up through this gas lift mandrel, and that always has the kickover arm aligned with the gas lift valve uh, uh, landing port. And again, you have to hammer this in place. That's called jarring, because if you can see here, there's a couple of metal jars where sort of it has a hammering effect. So it's a force multiplier to enable this sort of activity. So that was setting a gas lift valve. Now we're going to pull that gas lift valve. So they've reset the kickover tool, and now they've run it in the hole, and now they go past the gas lift valve, because we want to pull up and we want to orient that kickover tool again. So it gets oriented. So you see it turning. Now it's going to kick over. And now it's lined up for the valve. Here's the fishing neck. So we're going to get them down on this. The profile inside that kickover tool would match whatever's on the gas lift valve. And now we're just going to jar it out. Again, this is a really tight fit on these elastomer seals, but when they get them, and on the bottom here is usually a bit of a tool catcher in case the gas lift valve falls off that latch. So, so that's pulling a gas lift valve. What this also allows you to do, because it's designed this way, wells can have multiple gas lift valves in them. You can run past one and go down to a deeper gas lift valve if that's the one you want to pull, if that's the one that's causing problems. So, yeah. Now, I think we have one more video. So this is just a little short video, and this is it's the same shock test, but it's just spliced together with a bit of downhole video. So, and this is a downhole video approaching a gas lift valve. So this is what a side pocket mandrel would look like as you're going down into the mandrel. You can see there's the fishing neck, and that's where you would have your kickover tool. You can't see it. You typically can't see it when you're running slick line, but you will be looking at your tubing tally and saying, okay, this is the depth I'm at, and as it goes through the mandrel, okay, now I need to pull up and orient and to pull the valve. So, yeah. Again, if you're looking at comparing gas lift valves to ESPs, if you've run an ESP, then typically you have to pull the completion to get the ESP out and change it out. So from an energy efficiency point of view, this is a much smaller operation, and from a risk point of view, this is actually a lot more lightweight equipment. Okay, so let's go to the next one. So that's pulling and running. And so just looking at our well, we got our perforations, our packer. You can have multiple gas lift valves, and what you're trying to do is, again, we are lightening the density so that it's changing the pressure, the ability to flow. So just have one slide on the. What does that look like on a gas lift valve design? There's software that can do this, so don't panic about the graphical interface. But when you're, again, this is a depth versus pressure, and this slope is say water density or reservoir fluid. This slope is our injection gas density. So it's much lighter. gas is way lighter than water or oil. And what from a design point of view, you want to take your injection gas and inject it at your gas lift valve as deep as possible, because that gives me the most lift. And in lots of offshore facilities where you're re-injecting the gas, well, you probably have enough pressure that you can get all the way to the bottom, and you only need one gas lift valve in the well. In facilities, say onshore or in sort of near shore areas, Gulf of Mexico, North Sea, you probably don't have that much in gas compression and that much pressure. So what you will do is you will add valves in the tubing string so that you only need to get the gas down to that first valve, and then it starts unloading. Then it starts bubbling. Then that valve closes and the gas moves down to the next unloading valve, and that starts bubbling. And so on, all the way down until your, what they call it. So those are unloading valves, and they have a nitrogen charged bellows in them to close them once you get the fluid level down. Then when you get down to your what's called your operating valve, which is where you're going to be putting your gas lift in as deep as possible based on the surface pressure you have on your gas injection. So that is gas lift. It's, again, a very simple idea. It's blowing bubbles to lighten the fluid column. The gas lift valves have been probably run for probably since the 1960s. So it's a proven technology, and I would say that, but still advances being made. Companies are really working on getting better and better check valves, better and better control, so that you don't have any liquid going back into the annulus. So and higher reliability. So still lots of development work going on. Very interesting topic, but this was just an intro on how they work, what they look like, some of the issues, and that's about it. If there's any questions, please let me know. You can if you're watching this as a webinar, some of the previous videos are on the YouTube channel, and it's YouTube at Ballycatter. And if you have any questions, you can email me, rod@ballycatter.com. You can come up with solutions or more topics. We spent quite a bit of time the past few weeks on artificial lift. I'd like to thank a lot of the geoscience people out there for hanging in there and sticking through the mechanical stuff. Next week we'll talk about drilling wells and what it takes to drill a well, how you start, the whole well architecture, and just how that process works. We'll start with onshore, and hopefully we have some time for offshore. If there's no other questions, okay. Good night, and see you next week. Thanks a lot.